Good evening and welcome to the University of Tasmania's Island of Ideas public talk series. I'm Professor Jason Smith from the School of Natural Sciences, and I'm the head of chemistry there as well. I'm delighted to host this evening's talk, Plastic Inside and Out. Tonight we meet on La Truida, Tasmania, in Nipaluna, Hobart, the unceded land of the Palawa people, the traditional custodians of this land, sea and waterways. As we meet beneath Kenyani, Mount Wellington, and talk about the impacts of plastic on our bodies and environment, we reflect on the Palawa's deep history and custodianship of this place. Long before the synthetic materials we've come to know today, Australian Aboriginal and First Nations people developed nature's earliest, what we might call, plastics, by combining resin from grasses and trees with ash, charcoal, and even kangaroo dung. Using this substance, they would build and bind tools such as spear points and axes. This ingenuity reminds us of the value of Aboriginal knowledge systems, resourceful, place-based, and enduring. These were sustainable technologies embedded in culture and country, challenging us to think differently about the materials we create, use, and discard today. We pay our respects to elders past and present, to those who were denied elder status, and to Aboriginal people with us this evening. We stand for a future that profoundly respects and acknowledges Aboriginal perspectives, culture, language, and history. That history puts tonight's discussion in context. Our modern plastics are also human inventions. And while considered breakthrough discoveries at the time, and changed society and how we live in many ways, their legacy is profoundly different. Persistent, toxic, and now embedded not only in our environment, but within our bodies. The Island of Ideas series exists for conversations like this, where science, society, and responsibility collide. Plastic is everywhere, wrapped around our food, woven into our clothes, drifting through our oceans, and now, as science is beginning to show us, within our bodies and most living things. We've long thought of plastic as a problem of waste, something to clean up, recycle, and keep out of sight. And certainly I know myself growing up, and many of us would have known and be familiar with various campaigns, such as the Keep Australia Beautiful campaign, with slogans such as, "Do the right thing." But when it comes to plastics, what is the right thing? So the questions before us tonight are urgent. How widespread is plastic? And what impact does it have on our health? What is being done to keep us safe? And what must we do to protect ourselves, our families, and our communities from potential harm, now and into the future? I'd just like to take this time to acknowledge that Associate Professor Joanna Vince was originally scheduled to speak with us this evening, but unfortunately, she is unwell and cannot join us tonight, and we wish her a speedy recovery. We do, however, have an excellent speaker and a panel of one to explore these questions with. Dr. Jack Orty is a lecturer and researcher at the Tasmanian School of Medicine and a core member of the Adrift Lab research team, which investigates how microplastics contribute to disease. His work focuses on inflammation, and the brain, exploring the pathways through which environmental microplastics might influence conditions such as Alzheimer's disease. Originally trained in anatomy and neuroscience at the University of Otago, Jack went on to complete a PhD that combined botany and neuroscience. A bit of a difference there, studying the effects of synthetic cannabinoids on brain inflammation. His postdoctoral research at Otago and later at the University of Manchester expanded into inflammation biology, including hydrogen sulfide signalling, immune cell behaviour, and the role of the inflammasome in Alzheimer's disease and age-related cognitive decline. Now based in Tasmania, Jack's research spans cell models, animal studies, and fieldwork on remote islands, where his team has documented plasticosis, a disease in seabirds caused by plastic ingestion. He is investigating whether similar inflammatory processes may be occurring in humans, routinely exposed to microplastics through food, water, and air. Beyond the laboratory, Jack is passionate about science communication. I'm sure we'll see that come through this evening. He regularly visits schools, contributes to community radio, engages the public in conversations about the science of microplastics and health. To talk to us tonight about the global experiment that perhaps we're all unknowingly part of, please welcome Dr. Jack Orty.
Wow. Okay, so I'm going to actually start with a little bit of a warning, because my goal here is to turn you all into plastic activists. I want you to be aware of plastics, see plastics, and be concerned by plastics. But that comes with a huge warning. This may ruin every walk you go on from now on, and I'll show you why. I'll show you why. Now, the University of Tasmania runs a very clean campus, because it took me 5 minutes to pick up this amount of plastic, which is much more than normal. Normally it takes me about 1 minute to get that much plastic wandering around the bushes, much to my wife's enjoyment. And once you become a plastic activist, you can't help but see plastic. You walk down the beach and suddenly you'll see plastic in every patch of seaweed, all tangled up, and it starts to infect your mind and your pockets, because everywhere you go, you're picking up plastic and stuffing it into your pockets, and you end up with this. I will say, sometimes it's fun. You find amazing things, and this time, I found a passport. That's pretty good, so I'm going to have to report that to someone later. Okay, I want to start with definitions, and definitions are tricky. Let's just do a simple example. You might think the definition of a chair is something one person sits on and it has 4 legs. That seems like a reasonable definition. Here's a picture of my wife riding a chair up a volcano. She's having a lot of fun there on that chair. It's quite a lively chair, that one. So we need to be really careful with our definitions, and it's actually very hard to define things. An amazing discussion, and we didn't come to a conclusion, but I'm going to attempt to roughly give you the definition I'm working with. So this right here is a molecule. It's actually called an ester. And that ester here, this molecule, is actually responsible for the flavor of cinnamon. Isn't that nice? That is a molecule, it's an ester. But let's connect a bunch of these esters together. Many esters connected together in a chain. Then we end up with polyester. Boom, nice and simple. Poly means many. If I'm a polyglot, I speak many languages. If I'm a polygamist, my wife is very angry with me. So we're going to be very careful when we're using poly and when to use poly, but this is polyester, which is a polymer. Mer just means part. Many parts in a row makes a polymer, and some polymers are plastic. Some polymers aren't plastic, so there are natural polymers. This is DNA, this is a natural polymer. Cellulose in plants is a natural polymer. But my definition of plastic would be a polymer that's been changed or created by humans in such a way that that kind of compound or chemical hasn't existed, and we are now using it in our environment. So it's a new chemical structure that we're being exposed to. From a health perspective, that's important. Our body hasn't been exposed to these polymers before. And I'm going to tell you something that might surprise you. Plastics are actually amazing, right? Here we have a 4-gram plastic bag that costs less than 1 cent, and it can carry 20,000 grams of material. That is phenomenal. As a material, that's amazing. And that's perhaps why we've used it so much. And plastics had an amazing start. This is one of those Aboriginal tools we talked about, made out of resin. Now, this is a resin that's been chemically altered to change its properties, and so it might loosely fit the first definitions of plastic. Plastic also had a good start with this. This was one of the first uses of plastic, celluloid. We made plastic billiard balls, and that too was awesome. And the reason why it was awesome was because of where we got them before we invented celluloids. We got them from tusks and ivory. And so Joan Hyatt wanted to replace this with another source. And celluloid is actually made from cellulose. It's made from plants. But then we went a little bit out of control. And this is what I like to call the mind the gap problem. And the mind the gap problem goes like this. We will invent something or discover something. And as humans, we invent something and discover something and we think, let's just use that everywhere. Let's go. We've discovered something. This is amazing. We've invented something. That's amazing. Let's roll it out. And then sometime later, the gap, we come across the ramifications. Hey, there was a good metaphor there. There was a gap there, right? The invention and the discovery and the ramifications. Now, there's lots of examples. Think CFCs, asbestos, many, many examples. Two of my favorite is we invented a machine that can create X-rays. Wonderful. And wealthy people thought X-rays invigorated them. So they would get a morning whole body X-ray just to invigorate them. Then we learned the ramifications after a scientist wanted to know what would happen if he held his finger over the X-ray for a minute every day. He had to stop when he started seeing the bone, right? So we learned that ramification. Another one is we discovered radium can make glow-in-the-dark substances. And radium is a very radioactive material. And so we would paint it on the watch handles using a thin brush. So now our watch handles would glow in the dark. And the women in the factory, they were called the radium girls, were actually instructed to lick the brush into a point in order to paint the radium onto the watch handle. And this actually went on for a very long time, even though they saw the incredibly high rates of cancer going on. And so that's one of those gap problems, and we're now learning the ramifications. I think we're now learning the ramifications of plastic. Now, I'm going to show you where this plastic came from in a minute, but needless to say, it's not a great place. We're starting to learn these really negative effects of plastic. But my research career is focused on one process within the body mostly, and that's inflammation. Inflammation. Now, inflammation has four main signs, and that's redness, swelling, pain, and warmth. Those are the four signs of inflammation. And when I say inflammation to you guys probably think of something bad. I don't want inflammation. And that's actually what we've thought for most of human history. Here's a Greek pot that's from 400 BC. And the Greeks wanted to stop this inflammation, but they saw the swelling and the redness, and they decided that inflammation was caused by having too much blood. So the obvious solution to inflammation was draining blood. So on this pot here, we can see a doctor cutting into the arm of his patient to drain the blood in order to get rid of the inflammation. And this practice continued for a very long time, including this fella. Anyone know this fella? This is George Washington, the first president of the United States. And he fell victim to what I might call doctoritis. He was unfortunate enough that he could afford 3 doctors. And so he got influenza. Along came the first doctor, drained about 1 liter of blood. Along came the second doctor, drained about another liter of blood. Along came the third doctor, drained another liter of blood. They also thought he might have had too much green liquid, so they gave him mercury pills to induce vomiting. He died the next day. So this practice of trying to get rid of inflammation in some way probably killed the first president of the United States. But they were actually onto something. Inflammation might be a little bit bad, right? So I'm going to show you this experiment. This experiment, they took a little skin biopsy from a mouse, and they kept it all very sterile, and then they watched it heal over a certain amount of time. And this was the normal healing rate. 2 days later, you can see not much has happened. But then they took mice and they actually stopped them from engaging in an inflammatory process. So they stopped these mice from inducing inflammation, and that's how much it healed. So there was something bad about inflammation. And there's many, many things that might be slightly bad about inflammation, but I'm going to give you one example. The primary immune cell that rushes into that site there sprays a protein which produces bleach. And I don't mean a chemical like bleach, I mean actually bleach into the area. And it does it for the same reason we use bleach in our toilet and in our bath, is to sterilize the area. The immune system is always assuming there might be an infection. We better sterilize that area just for safety's sake. But if we can stop it from spraying bleach into a wound that we know doesn't have bacteria, then we can accelerate the healing process. Now, doctors were big believers in this, in particular into head injury. Because you imagine you sprain your ankle, it swells up, it goes red, it goes painful, that's kind of bad. But imagine your brain swelling up, and it's inside the skull. And now the swelling is pushing against the skull. That seems like a bad situation, and you've got bleach being sprayed into there. So doctors believed that we should inhibit that inflammatory response with anti-inflammatory steroids. But eventually somebody said, wait on a minute, we haven't actually run a clinical trial on this. We haven't run a clinical trial. So they organized a clinical trial, and doctors resisted it. They said, I know my patients get better when I take a person who's had head injury, like this car crash. I know my patients get better when I give them anti-inflammatory steroids. But eventually we managed to convince them, to roll out a clinical trial. And they found that the absolute numbers of people who died increased by 3% in the sterile anti-inflammatory group. So that means 3 in every 1,000 people, 3 in every 100 people died because of the treatment the doctors were giving them. So why is that? Well, inflammation does bad things like spraying bleach, but inflammation does good things. Here is one of our little immune cells, and he is eating that debris. He's cleaning up that debris. So there are a lot of good things that the immune system can do and some bad things that the immune system can do. And that's what my research has focused on for a very long time, was how do we flick the switches inside these cells, these molecular controls that we have inside a cell? How do we flick them on and flick them off just to get the right immune response? And then many years ago, people started talking about this problem of plastics. And I was aware that there is one switch inside immune cells that you really don't want to leave on. You don't want to turn it on and not be able to turn it off. And I was very concerned about the concept of plastics, because how would the body break it down? How would the body get rid of it? I couldn't see a way. And so I imagined that plastics, microplastics in particular, might come in and turn this inflammatory switch on and never turn it off. How could we get it to stop? And that's something I was really concerned about. And so I did an experiment. Now, this is a very Friday afternoon experiment. This is not a Nobel Prize winning experiment, but I took some immune cells, and then I took a Swiss Army nail file, and I took it to a plastic container to generate my first batch of microplastics. So I had my little Swiss Army knife, and I was rubbing it across, and I didn't know how much I'd created, but I was just saying, hey, let's have a look. And I put this on my immune cells to see if it would turn on that inflammatory switch and not turn it off. And this is the result we got. Now, fortunately, I had some immune cells that lacked that switch. Genetically, we deleted that switch from them. And so on the y-axis there, we've got toxic inflammation. On the x-axis, we've got our treatments. And over on those last 3, I've genetically deleted that molecular switch that turns on that toxic inflammation. So here we can see that my nail file had managed to induce a toxic inflammatory response from those plastics. I then went on, obviously, to do much more thorough research on these microplastics, and we found amazing things like the plastic type changed the inflammatory property. But this might surprise some people. The plastic color changed the inflammatory property. And that's because plastics contain all sorts of other chemicals that we don't know what they do. And in fact, companies don't even have to tell us. So we have contacted the companies who have provided this plastic and said, did you know your blue plastic is incredibly inflammatory? Can you tell us what's in that? And they say, no. Interestingly enough, glow-in-the-dark plastic is one of the most inflammatory. And for some reason, that makes sense. I'm like, if it glows in the dark, going back to the radium girls, it's probably going to be very inflammatory. But I wanted to get some real experience, not cells and dishes, and not mice in labs. I wanted to explore what was happening in the environment. And so I teamed up with the Adrift Lab. Jennifer Lavers and Alex Bond are the amazing people that are the head of that lab, and they let me join with enthusiasm. And for this, we got to fly out to Lord Howe Island, which is halfway in between, well, maybe a third of the way between Australia and New Zealand. And it's a fantastic place to do research because the animals here are mostly unaffected by some of those other things, like rats, air pollution, that kind of thing. They're sort of in a very clean place, but they are affected by the plastics in the ocean. So we can explore what's happening to these birds that are on this island to understand what might be happening to us and to understand what's happening to wildlife out there. These are the birds. They're called toa nui in Māori. They're also called sable shearwaters, is sort of their formal name. And they are, you grow to love them. They're a very plain bird. You look at them, but now you start to love them after a while. They make this lovely sound that goes, pick me. It sounds like they want you to pick them. They go, pick me. And this is what they look like when they're just starting to fledge and they've got their fluffy down feathers. But then they come out of their burrows, and this is my PhD student who's actually sitting right there. She deserves a round of applause. Can we give her a round of applause because she did a lot of this research? Alex to Jersey. So here she is here, and she's returning one of the chicks back to the burrow. But it's a sad state of affairs, and I don't think, I've been going to the island now for 5 years, and I don't think every year we have a different crew, and I don't think anyone has not cried when they've come to this island. So the birds, they leave their burrow, and now they're supposed to fly to Japan. But some of them have been so affected by plastic that they can't fly to Japan. They can't even fly. So they try to walk, and they'll try walk to Japan, and they'll walk into the water, and the waves will wash them up. Sometimes they might be able to fly a small distance, and then the waves will wash them up. And it's a really tough thing to see. And you'll see their footprints go down the sand, and then you'll find one washed up on the beach. So every morning we would go out and we would find these birds. Some of them had died, but some of them were close to death. So the best thing we could do would be to euthanize them. And so here's a very underweight bird that's been affected by plastic, and Alex is naturally upset, as we all were every year. It's one of those things where my colleagues go, how was the holiday? Because I've been to Lord Howe Island, and they don't understand that we've been working for 16 hours a day, analyzing and studying these birds and trying to help them, and the incredible emotional toll that's on there. So here is, on the left there, we have a bird that's been hit by a car, and it was about to fly to Japan. It's been hit by a car. And on the right, we have a beach wash bird that was full of plastic. So you can see that there's a huge difference in the condition of the birds there. Here we are at the lab. Up the back there is Jennifer Lavers. There's my PhD student, Alex, and there's me. You'll notice we're not wearing gloves. That was very hard for me. I came from the medical field, but we don't want to contaminate our samples with the plastics that our gloves are made out of. And we're analyzing the tissues in these birds. Now, the following is going to be real graphic. So if you don't want to see what we're about to see, it's a very challenging thing to see. I think it's worth seeing, because hopefully it'll make you angry, and then it will ruin every walk you go on from now on because you'll be picking up plastic. This is one of the worst birds we had. I mentioned that it was 16-hour days. A lot of that time is just counting and sorting plastic. On my first season, we found a Lego man, and it was an astronaut. And that astronaut was only made between 1970 and 1975. And that plastic's still around, and it's killing animals. And I had the thought, this may not be the first animal that astronaut has killed, because it could kill the bird, and then the bird would rot around the plastic. Then the plastic would wash out into the ocean, and then another animal might come and pick it up. So that's where that picture came from. And you can see a lot of lids, tile spaces, oyster spaces, many fragments. There's a mysterious item that keeps popping up, and we can't figure out what it is. You do little things like that to kind of, I don't know, bring a smile to your face. You're like, oh, look, it's that weird little circle thing that we keep finding, and we have no idea what it is. A lot of nurdles. Now, nurdles are the raw plastic that we transport around the place to then turn into other things. So they're these tiny little balls, but shipping containers fall off their boat full of nurdles, and the nurdles go out into the ocean, and we still find those. And I'm going to come back to that in a sec when I start talking about solutions to this problem. So what did we learn? This is Alex's favorite bird. So what did we learn? We learned a lot. The first place we looked was the stomach. That made the most sense, right? And if you actually look at that one on the right there, that was the first stomach I ever opened up. And I immediately said to Jen and Alex, that's inflamed. And they said, how did you know? Because they're environmental scientists. They're not familiar with what the body looks like on the inside. But you can see how it's puffy. You actually can't see the ridges in the stomach there. And that's because it's puffed up and the ridges have gone from the puffiness. And you can see it's shiny. That's because fluid is rushed into the site and the cells have rushed into the site and it's gone puffy. The other thing I want to point out to you is you might think plastics are pokey. So the plastics are poking the stomach, and that's how it's causing the problems, right? But have a look at this middle one. That's squid beaks. And those squid beaks are actually still sharp enough to cut your skin. So it's not just that it's pokey. These stomachs actually evolved to deal with pokey things, like squid beaks. It's something else about this new substance that we've made, which is plastics, that is doing unique pathological things to the stomach. Now, this is a really thin section of a stomach that we've put on a glass slide and we've stained it and we've put it under a microscope. Now, what I want you to imagine is the left-hand side is where the stomach is, and those are actually little tubes that pump stomach acid out into the stomach, right? Now, the blue is the connective tissue, and that holds everything together, and that's really good. But just like when you cut your arm and you might get a scar, and that scar is tough, that's a buildup of connective tissue. So let's have a look at a plastic-impacted bird. And what we can see is that blueness is huge, right? So this is the scarring that's going on in the stomachs of these birds. And we define this as plasticosis. So if you breathe in silica dust, your lungs become inflamed and fibrotic. That's called silicosis. If you breathe in asbestos, your lungs again become inflamed and fibrotic. And that's called asbestosis. If you drink too much alcohol, your liver becomes fibrotic, and that's called cirrhosis. So we use that same suffix there, plasticosis, to define this new inflammatory fibrotic disease that happens when animals consumed plastic. But we also found little bits of plastic that would float around the body and embed in other organs. This slide didn't render that well, but this is a liver section. And there you can see a shiny bit of plastic embedded in the liver, and it's surrounded by immune cells, all reacting to that. That's that dark purple there. So we know that there's microplastics floating around. We're also very concerned about what chemicals are coming out. Plastics are all full of horrible chemicals that might leach out and affect the body in other ways too. But these birds had died of plastic. That's a really extreme response. So we actually wanted to start to look at some healthy birds to see what a moderate or lower amount of plastic, a non-fatal amount of plastic, what does that do to the body? So we did a study where we take these birds and we actually flush the plastic out of the stomach. We put a tube down their throat, we fill it up with water, and then we induce a vomit. And in that tray there, you can see the plastic. You can also see the love for these birds, and Alex and Jen, they just love these birds. But now we can actually study healthy weight birds that are above 600 grams, are ready to fly to Japan. These guys are healthy birds. And we'll flush their stomach to figure out how much plastic's in their stomach. And then we take a little blood sample and we measure over 2,000 molecules in that blood and try and figure out what's going on in there. And this is a little bit of a break to the scientific method. The traditional way to do science is you come up with a hypothesis, then you test it, right? That's the scientific method. But we're moving now a lot, and particularly biomedical research, to big data. We're not asking one question at a time. We want to look at a huge amount of data to figure out what's going on. And here's the graph, right? So this is, each line is one molecule that we've measured in the blood. right? And this is the molecules from the birds. This is the molecules that the birds are producing in response to the plastic, right? And so you can see there's over 2,000 molecules there, and the levels are on the y-axis, right? But what do you do with that data? That's a heck ton of data. So just to give you an impression of what we did, what you do is you look for a signature. So if we go along here, we can see this is the approximate signature that we get in this big data. Then you can actually upload the signature to existing databases and say, what matches the signature that we have? So here we have a signature that I got from a public database for cancer, a particular kind of cancer, and we can line that up and go, does that match? And we can say, not really. So this one, it didn't match, right? But we upload the signature, the peaks, the significant peaks and the significant troughs, and we uploaded the signature to the database to see what it matches. And surprising to us, one of the matches was dementia. And we absolutely did not expect this. The brain is normally protected by this thing called the blood-brain barrier. It doesn't let things in. The brain is precious. And we absolutely did not expect a match to dementia. We expected kidney failure, liver failure, which we did see, a lot of kidney damage, a lot of liver damage. We saw stomach damage, obviously, but we also saw brain damage. In fact, one of the signatures we saw was a decline in this marker that was actually kind of discovered in Tasmania to correlate with age-related cognitive decline. And that was done by James Vickers over at the Wicking and Jess Collins. And they showed that a moderate decrease in this marker was associated with age-related cognitive decline. And we saw a massive decrease in that marker. We saw about a 50% decrease in the marker. Now, the surprising fact here is these birds are 100 days old and they live to 37 years old. So to see these markers of brain damage and dysfunction was very concerning at this day, at that age. And just to give you an idea about dementia, there are many kinds of dementia. This is one. This is called Alzheimer's disease. Dementia is essentially a disease in which your brain cells die. So on the left-hand side, we can see what a healthy brain looks like. On the right-hand side, we can see what severe Alzheimer's disease looks like. And we have a concern that we've got signatures of neuronal death in these birds that have been exposed to moderate amounts of plastic. Now, I've been talking about my research for a long time, so I thought I'd do a little break and talk about one of my favorite studies ever. And this favorite study involved a unique international collaboration where we all decided to drop nuclear bombs. That was an interesting research decision. So in the 40s, the 50s, and the 60s, we dropped many, many nuclear bombs, okay? And here's a nuclear bomb. And then in the 60s, we said, let's not drop nuclear bombs in the air anymore. That was probably a good decision. But we decided to do it underground. But this caused an interesting thing. It caused our atmosphere to become radioactive. And our body is made from the atmosphere. Now, that sounds a little bit weird, but the plants take in carbon dioxide from the atmosphere and they turn it into themselves, right? So plants breathe in carbon dioxide and then they turn that into themselves. Then we eat the plants and we take that same carbon that was in the atmosphere, went into the plant, now it's in us. So we are made out of the atmosphere. And that led to an interesting thing. If you were born in the 60s, you were born with a very radioactive body, which is quite interesting because the atmosphere was radioactive. Now I'm going to demonstrate what then happened to make some amazing discoveries. Oh, look at that. Can we get the lights off? Oh, the power. Okay, so let's imagine this glass jar is the 1960s, all right? And we drop in a lovely nuclear bomb there. Oh, look at that, that's brilliant. Just a little side note, I just put detergent in there. Detergent puts fluorescent compounds in there to trick your eyes to thinking that your clothes are brighter, right? Which is interesting. How do you think they did long-term testing to see if that killed any animals or anything? No, of course not. That's the attitude. Oh man, my hands look like a murder scene. Okay, now the nuclear bomb goes off And then we need to spread that radioactive material all throughout the atmosphere. So this is how radioactive our atmosphere was in the 60s. But then the radiation declines. Now, it doesn't decline because the radiation dissipates. The half-life of this radioactive material is thousands of years. Why it declines is because the radioactive carbon in the atmosphere gets soaked up into the ocean, to the forests, to the crops, and our bodies, okay? So this is how radioactive it is in 1960s. This is how radioactive it is in the 1970s. This is how radioactive the atmosphere is in the 1980s, 1990s, 2000s, and today. So hopefully we've got a lovely little curve here. So we end up with a timeline of radioactivity, right? Now, someone who's born in the 60s, their whole body is this radioactive, right? And now somebody, as they age, parts of their body are going to be replaced, right? Your skin is only about 6 weeks old. And that is why if you ever need a high protein meal, you could maybe lick the top of your bookshelf to lick all the dust up, because that is about 50% human skin cells. Because we're constantly replacing our skin, right? So if we have replaced our skin, it won't be as radioactive as things that haven't been replaced, right? So now, I'm going to ask you guys a question, okay? There's this great Greek philosophical question, and it's called the ship of Theseus, right? Now, the ship of Theseus is a ship that leaves a Greek port, and then its mast breaks down. So then they replace it. Then its decks break, and they replace that. Eventually, on its journey, every part of the boat has been replaced, and then it gets back to port. And you ask the question, is it still the ship of Theseus? Or is it not the ship of Theseus because every part of it has been replaced? So my question to you is, do you guys think you are a ship of Theseus? Do you think every molecule in your body has been replaced since the day you were born? Any thoughts? I was told, if you think everything has been replaced in your body, can you hum? Oh, I'm seeing a strong consensus. Well, let's jump back to the experiment and see what we find out. In the experiment, somebody was born in the 60s, right? They died in 2010. Let's sample different parts of the body and see how radioactive it is. Okay, if you see what I've got. So they sampled the skin, and the skin came up the same radioactiveness as today, saying that that has been replaced recently, right? It is made from recent atmosphere. They sampled the brain, and the DNA in your brain, in your neurons, was the same DNA as the day you were born. Those molecules have been with you since you were born. Those humble molecules inside the nucleus of your brain cells. And I find that amazing, because if you were to ask a scientist, where might the soul be? They might say, well, in your DNA and in your brain. And that has been with you the day you were born. But it comes to a very serious and worrying conclusion, which is if you lose a neuron, it's the most precious cell in your body to lose, because it's been with you since the day you were born. So the idea that plastics could be attacking and killing these cells is scary. Okay, so what do we do about it? What do we do about it? And that's an interesting question. I'm sort of filling in for Joanne here. She's the policy expert. I'm the person discovering how bad it's for you. So I'm out here thinking as radical as humanly possible, beyond realistic policies. But the first thing I want to get to you is this advert here. It's called the Crying Indian advert. It was made by Keep America Beautiful. There it is down the bottom. And this ad campaign was funded by Coca-Cola and Pepsi. And it was funded at very similar time that they were switching from glass bottles, which they washed and cleaned and refilled, to plastic, right? And in the advert, a plastic bottle's dropped, the Indian picks it up and a single tear rolls down his cheek. But I think the perfect metaphor for how cynical Coca-Cola and Pepsi are by running this ad campaign is, this actor was Italian. And what they wanted to do was to shift the blame. They were shifting from a reusable glass bottle to a single-use plastic bottle, but they wanted you to blame yourself for the rubbish that's out there in the environment. And I'm here to tell you it's not your fault. I don't think it is your fault that we're in this situation, right? It's people like Pepsi and Coca-Cola who are switching from these green solutions. And so what's the answer? Many people may say the circular economy. Now, the circular economy is a brilliant idea where things go round in circles, not in one direction to the landfill or to the ocean. Now, the problem with the circular economy is that it's leaky, right? Just look at the basket of stuff I just pulled out of the bushes at UTAS, or the ocean, or the birds. The circular economy leaks. Now, if we know that the circular economy leaks, we should design our products to be okay if they leak. We should also design our products to be very good at going round and round. Plastic is not great at going round and round in the circular economy. Plastic, those long chains, degrade as they go round, and they accumulate, or who knows what kind of chemicals. And there isn't some magic machine which you can put in to measure all the chemicals in a substance. So if we recycle our plastic, we don't know what chemicals have been built up, have accumulated, have been incorporated into our recycled plastic. Plastic is not a great substance for a leaky circular economy. But when I was a kid, when I wanted to get milk, we had a milk boy who delivered glass bottles, right? And they would wash those glass bottles and refill those glass bottles with milk, and then they would be delivered back. And it was a wonderful job to have when you were 16, was to be the milk boy and run around. That's the circular economy. Glass is one of those materials that can handle a circular economy. There's other ones potentially. Aluminium. You can melt down aluminium and reform it as many times as you like. Plastic may not be the one. I think in a leaky circular economy, we need to eliminate plastic as an idea of a solution. Just to reinforce this, how much time have I got? Oh, I'm late. Okay. Just to reinforce this is the global estimates. Australia is about the same. This is what percentage of plastic gets recycled currently. It's about 9%. A huge amount is incinerated. Australia and America used to send our plastic off to China to be recycled, but it was being incinerated. And now we're sending off to Indonesia, and probably similar things are happening in those places. So recycling, although it makes us feel better, unfortunately, it makes us feel better about buying the plastic. And so we continue to use and continue to buy the plastic because we think it's okay, it's going in the yellow bin. But maybe that's not the answer either. I think this is the main answer, right? If we're trying to stand up against Pepsi and Coca-Cola, it's very hard to do it as a group of individuals, but I think governments can, and they do. You know, one of the states put in that 10 cents for popping your bottle into the recycling. It's actually the company that has to pay those 10 cents. So naturally, they sued the state who rolled that out immediately, trying to block it. But the state government fought it, got it through, and then Tasmania was one of the last to follow that state. So I think the most important thing is vote. You can also vote with your dollars, right? So I think actual political voting is super important. Political activism is super important, but also voting with your dollars if you can, right? A synthetic t-shirt from Kmart costs $5. A wool t-shirt from a quality store made of Australian wool might cost $100, right? So saying financially, oh, just choose the green solution is a difficult thing to ask, which is why I again go back to, I think political avenues are the most important avenues. Now, if I was to just say one personal thing that I think This is what I did, and one personal thing that I think you guys can do to avoid microplastics. I'm actually going to give you some homework. Here's your homework. Go into a room on a sunny day, shut the curtains, turn out the lights, crack the curtains, get just a beam of light. Get your favorite polar fleece jumper, which is made of plastic. Walk up to that beam of light and just tap your shirt and watch the hundreds, if not thousands, of microplastics float off that synthetic top. So if I was to give you one piece of advice, is that most clothing is synthetic. Almost all soft toys are synthetic. And when you visualize those synthetic clothes, I want you to visualize the crude oil that came from to make that plastic. And imagine the baby breathing in that microplastics that are made from crude oil. That would be the one thing I would leave you with, is clothing is one of the sneakiest sources of plastic out there, and we're all breathing it in. A recent study came out saying you breathe in 68,000 microplastic particles a day. I think that's an underestimate, because there's an Australian study that showed about 40% of household dust is microplastics. So maybe don't lick the top of the bookshelf. I actually take that back. It's not good. Okay, I think that's it. Thank you very much for listening to my talk.
All right, thank you very much for that, Jack. Certainly a mix of learnings there this evening. Plastics, we got a little bit more, a little bit of radiochemistry involved as well. I know certainly coming to tonight, I did look at my suit to see what it was made of. It is mostly wool, but not all wool. Yes. Okay, so we'll open the floor to questions now. At the moment, we'll start the questions. Do we have any from the floor at the moment? And then we'll move on to the online. Yes.
You've mentioned that the clothing is a major source of plastics in ingestion. What other sources have we got to consider?
Yeah, that's a great question. And we're still tracking it down. Inside the house, I think you really are looking at carpet and clothing and drapes as the major source. Outside the house, it's very clear what number one is, and that is car tire wear. So the car tires are wearing down, a lot of synthetic tires, and they generate microplastics that go into the air. And that definitely seems to be the number one outside the house.
So I'll just take one from online here from Kwan. So I'm saying this one's obviously for you, Jack. How does plastic contaminate nature? And are they present everywhere? What is the root cause? And perhaps you've probably maybe just answered that to a certain extent.
Yeah, so we have found them in Antarctica, on the top of Mount Everest. We have found them inside wombs and breast milk. We have found them everywhere. Synthetic tea bags. You're literally dunking plastic fabric in your tea a lot of the time. So this is actually one of the challenges. To establish human health effects, you normally look for differences in exposure. Who's high exposed and who's low exposed, and then look at the disease prevalence. So asbestos miners had high rates of lung cancer, so that's how we started to build that connection up. I'm concerned that all humans are kind of equally hugely exposed to plastic. So it's hard to find that high group and low group. I have grand ideas of going to factories that make synthetic clothing and having a look at the employees in that one. But yeah, that's going to require a lot of forms.
Okay, we've got a question from over on the right-hand side over here.
I was just wondering if floor varnishes have got plastic in them, particularly when they start to break down with the sun.
That's a great question. In fact, what I would encourage everyone to do right now is to look around the room and see if you can find something that isn't covered in plastic. Because unfortunately, polyurethane, that's a synthetic polymer. And that's what we varnish our floors with. And our walls and those drapes are probably synthetic. That screen is synthetic. 80% of clothing is synthetic. That goes up if it's a cold day. There's not many natural material warm jackets. Your chairs, the carpet. It's very difficult to actually find something not covered in plastic in a big space like this. Great question.
Just over here on the left-hand side.
Thank you. There are different types of plastic, aren't there? So, for example, if you buy a water bottle in an outdoor sports store, that's better than a reusable throwaway single-use plastic, isn't it?
Well, yeah. So I have a PhD student, Oshin, who's exploring this and is sort of generating microplastics from a range of sources. Polyamine, which is nylon, and PVC seems to be incredibly bad, but we kind of already knew that. We haven't found a non-inflammatory plastic, unfortunately, but I will say reusing will reduce the environmental exposure of plastic. So avoiding single-use plastic is good in that respect. There are metal sports bottles, so I would lean that way, and I certainly try to.
I've got an online one here for you from Bronwyn, and she's asking, what are the alternatives of plastic bags used for things like meat and fresh products? Are they out there yet?
This is a great question. I actually encourage people to do this. Try go on YouTube, and there's like a trend where people try and make no rubbish within a month. And it's incredibly difficult. It is so difficult. But what you have to do is call up your butcher or the supermarket and say, can you wrap some meat in butcher paper and I'll come pick it up. And so you have to go to that level of extremeness to get rid of it. This is kind of why I say it's not your fault. It's almost impossible to just operate in today's society without engaging and consuming in plastic. Do your best, but yeah, we need to push for legislative change rather than focusing on individual decisions.
A question from down in front over on the right.
Plant-based plastics have become quite common recently, which is nice because they're renewable. But in terms of the health impacts, are they any different?
We have not found so. That we find them, we've done polylactic acid, for example, which lactic acid, natural thing, but you string it together. It seems to be that the particle itself is a problem. It's sort of an indigestible particle that the body can't really do anything with. It activates the particulate response in our body, the same particulate response in silicosis, in asbestosis, yeah, as the microplastics. So I'm not sure if naturally sourcing is going to solve that problem. It does mean vague things about not having to mine crude oil, but it's very limited. On that, bamboo socks are not made of bamboo. So they are made of bamboo, but what happens is we digest the bamboo down into basically little carbon elements, and then we string them together with a plasticizer. And so eventually bamboo socks gets turned into a vat of clear liquid, and then it gets squirted at high pressure into sulfuric acid, which acts as the polymerizer, and it generates the plastic fibers from the bamboo. And we should have known that because those socks do not look like they're made of bamboo. Can we be honest? They're not brown, they're not sticky. Yeah, so, and that's that complicated line between what is plastic and what's a synthetic plastic.
I've got one online here from Rachel, who's asking, what about the fact that they're putting recycled plastic back into road surface products? Is that just compounding the problem of tyre wear?
Yeah, so look, this again goes back to my opinion. There's this concept of greenwashing, which is where you do things to make us feel better rather than actually change the system, right? We'd rather feel, oh, they're now using my plastic bottles to make a road, than we'd rather feel, oh, so it's fine to buy a plastic bottle, but you're just feeling better. So what happens to that road? It's going to deteriorate, right? It's being exposed to UV over a long period of time. Microplastics are going to shed off that. Now, is that worse than the tar that already sheds off it? I don't know. But yeah, what I would warn is anything that makes you try and feel better by continuing to consume single-use plastics. Let's just try not to do that rather than make roads out of plastic, for example.
Okay, we've got
in my opinion.
One over here on the left-hand side.
First of all, I'd like to congratulate you on the work that you do at Lord Howe Island. I'm active in the space as far as politics goes and voting, and I'm interested in hearing what you say because I'm trying to raise awareness about the microplastics associated with the salmon industry. And as a sailor, I see it everywhere in the waterways around southern Tasmania. At the moment, our government doesn't have a policy on microplastics at all. And when I spoke to them about this and lobbied them, they weren't interested because they weren't convinced that this was an issue. Now, you're doing research in Lord Howe and what the impact of microplastics is having on shorebirds there. I can't imagine what the impact of the shorebirds here and the fish and the native animals in our marine. What can we do to try and raise that awareness, given that you're talking about it, more and more people are talking about it, even the WHO has a policy on it. What can we do as individuals to try and raise our government to start listening?
Yeah, so well, that's a huge question, how to get political movement. I am just an immunologist, biologist who sections in a laboratory a lot of the time. The one thing I'll say is I have actually read a couple of studies on this, and politicians, this is a weird study, but they compared the response to politicians to handwritten letters versus phone calls versus emails versus typed out letters. And handwritten letters changed the mood on the politicians the most. Obviously, voting is going to be a huge thing. And we're competing against people who pay money into the campaigns of it. But you're right about fishing. What some studies looking at the larger plastics say that fishing nets cause, by weight, some of the largest amounts of plastic pollution in the ocean. I would say that they're missing the microplastics in those studies, which might make up a huge amount. The other thing I'll say is I was on an advisory board for policy, and the best that the team was trying to come up with was put filters on washing machines to filter the microplastics before they go out into the ocean. One thing I'll say about that is, A, what are you going to do with the filters? You're going to put them in the rubbish dump. It's going to rain on the rubbish dump and get washed out. B, the size that we're concerned about are smaller than a human cell, because those ones can get inside human cells and flick that inflammatory switch on and not let it turn off, right? That, in my opinion, is the most scary microplastic. The filters that we have that can filter that out, filter at rates of like half a mil a minute. So it'd take like half an hour to filter that. We're not going to be able to put those filters on a washing machine. And that's just making us feel better. Oh, I've got a filter on my washing machine, filtering out the microplastics so I can continue to buy synthetic clothing. I really don't think that's the answer. Yeah, so right to your politicians, I got to stop talking.
I mean, certainly, one of the options you're saying is you can choose when you buy as a consumer, you can go for glass instead of plastic. But I've got a question here online that pretty much asks this question: do we always have that choice? And the one that's come up is certainly in the health industry and hospitals, and the amount of plastics that's used within hospitals and medical aspects. And is there anything that can be done in that particular space? Or is there a certain amount of this that we've got to deal with, and it's perhaps the collection side we need to do better in controlling it where we have to use it?
Yeah, the medical waste one is interesting. I have a gross study. Do people want to hear this gross study? It's going to freak you out a little bit. Okay, so the study goes like this. People report getting a bad taste in their mouth when they receive an IV bag of saline, right? And people report a worse taste the older the saline bag is. So some scientists did some studies on what residue was coming out of the breath of the patients who were receiving an IV bag. And you're not going to, you're probably going to guess there was plastic residue leaking from the IV bag into the saline. It was going into the blood. It was going around to the lungs, being breathed out onto the tongue, and they were tasting the synthetic chemicals from the IV bag. And so the older the IV bag is, the worse the taste was. Now everyone's going to not want an IV bag. Just ask for a fresh one. That's what I'd say.
I was going to say that. Can I have a fresh one? Can we start dating them?
Yeah, can we get a new one? So the one thing I'll say about that is, look, medical waste makes up a tiny percentage of the total plastic that's produced. And if you say we need IV bags, there's probably 1,000 Coke bottles per IV bag, maybe more, 1 million. I don't know what that number is. Let's focus on those low-hanging fruits first before we start talking about the medical side. The other thing is the medical side is incinerated, which is oddly a potentially mildly okay solution.
We've got a question over on the right-hand side here.
You haven't mentioned the effect of of BFAS and BFOS, derivative products, which are so ubiquitous. And some governments are doing something about that. Perhaps you might like to comment.
Yeah, that's a fantastic question. So he mentioned some of the chemicals that can leach out, like PFAS and PFOS, that can leach out of plastics as a problem. And the one thing I'll say to that is there was a study that came out that attempted to quantify the number of additives in plastic. And it came up with a number of about 300,000 potential additives in a plastic. And then moving on from that, you might have all heard of BPA. BPA, have you guys heard of BPA and BPA-free plastic? There was concerns, BPA activated the estrogen receptor. There was concerns that that can lead to huge problems. So they replaced it with BPS. The only problem with BPS is it activates the estrogen receptor better than BPA. So when we start talking about individual chemicals, it does get really difficult. It's likely that many of them do huge and varied things. And I mentioned, you know, this fluorescent thing that they put in that detergent over there. There isn't a strong regulatory process to get through in order to put a new additive out, a brand new chemical. I actually asked Joanne on the call, she's the policy expert. Let's say I want to put a new chemical in the lid of my Coke bottle. I'm running a new campaign. I want it to be hot pink. I've come up with this brand new hot pink chemical. I want to put it in the lid of my Coke bottle. What steps do I have to go through to get that approved? She said none. None. So, you know, we're walking we're rolling the dice every time we add these new chemicals in. And so, yes, you're right. There are some chemicals that we've really identified cause huge problems, and there's probably many more. And testing 300,000 is a big job that we need to do.
Does the current algal bloom in South Australia offer special research opportunities given the great loss of marine life? Thank you.
Yeah, that's a great question. And so Jen Lavers loves every bird ever, and Alex and I will regularly get texts from her saying there's a bird wash event. And what that means is that many birds, sometimes 100, sometimes more, have washed up on a beach. Can you go count them and look at them? And so Alex and I and Jen obviously have spent many weekends going out and looking at animals that have spontaneously died to see if there's plastic in them. Often they're too old to look at the physiological responses, but we can do simple things like quantify the plastics inside them if they've died of things like an algal bloom or plastic.
I'm going to combine two questions here from online, from someone who's anonymous and one from Megan. And basically they're asking if, well, first part is if we're born in the 60s, how can we reduce the accumulation of plastics within our body?
Yeah.
And the second question there is really, is the body capable of detoxing from microplastics? Is there any evidence from that? I mean, obviously you can look at a seabird, you can look at the size of those plastics, and they're probably very unlikely to pass it. I guess as kids, most of us maybe swallowed a plastic lid off of a pen. I don't know if they're still in us or not, but you know, are we able to pass microplastics that we are consuming?
Yeah, that's a great question. So if we eat it, I think we're very likely to pass it. If it's small enough, we're very likely to pass it. Our digestive tract is evolved to deal with problems, not plastic, but often problems like worms and all sorts. So it's covered in mucus. If you were to eat a dice or you know, a BB, or I imagine it would come through eventually. It might shed some stuff. But interestingly, in the birds that were eating plastic, we looked in their liver and they upregulated detoxifying enzymes like aldehyde dehydrogenase. So the liver is obviously doing some extra work to deal with those chemicals. I don't think it's digesting plastic though. I think there's chemical leachate coming out and the liver's responding by trying to detoxify the chemicals that have come out. I don't think there's much we can do about a plastic piece that's embedded in the liver, like I showed you, or in the kidney. I really think the only thing the body's going to do to that is surround it in a scar tissue to try and seal it off. And that's what our body's probably going to try and do.
I mean, somebody online did ask the question is, are we doomed, knowing all of this and the emotional toll? I will add one aspect. There are certain plastics are looking at being recycled. There are enzymes, organisms, we were talking about this earlier, that they've identified that can actually take plastics, particularly the nylons and the polyesters, because of their chemical structure, and can actually take them back to their basic, the same starting materials that they existed from. And so that is contributing to the circular economy. But again, as you said, there's so much leakage within there. You know, a plastic that has been collected is not necessarily a problem for the environment. And really that's just stopping, it's a sustainability aspect in there that you're no longer having to source raw material from fossil fuels. We've got a question up on the right-hand side.
My question is there many human trials looking at Alzheimer's and associated with plastics at all?
No. straight off the bat, no. There's a few problems. One, it's actually really hard to quantify microplastics. And so there are challenges we're trying to face there, and to actually know that a small particle is a plastic is quite difficult. So I'm sectioning brains and looking for the plastic is very difficult. The best human trial that I can tell you about is when you get a clot in your heart, they can actually put, doctors are amazing, they can put a little wire up your artery, screw it into the clot and pull the clot out. It's called a thrombectomy. Then we can look inside that clot. And this study looked inside the clot and they found 50% of those clots contained a microplastic in the core of that clot. Now, that made me worry, but I also, understatement of the year, that made me worry, but I was a little bit skeptical because again, it's really hard to find plastic. Really hard to know that a particle is plastic. They did use 3 separate techniques to identify that plastic, but here's where it gets really scary. The patients that had plastic in the clot were much more likely to have another heart attack than the patients who didn't have a plastic in the clot. I think that's the best study right now that shows strong human effects. The microplastics in there are initiating an inflammatory response, which initiates clotting factors, which causes a clot. And that biological reality, you know, you've got twice the risk of having a secondary heart attack, tells me that it wasn't lab contamination, it wasn't a mistake, it wasn't a misidentifying, because it's having a biological effect. They must have really identified that plastic, and there is something different about those patients compared to the other ones.
Question from over here in the middle.
Thank you. Look, you've done a great job of explaining the depth of the problem, and I guess the word that I think of is ubiquitous. So we're stuffed, right? Like the world, plastics are ubiquitous in every single solitary thing we do. I'm just wondering, with that in mind, is there any move by governments or international associations or industry associations or research organisations to come up with some sort of prioritised list of plastics that do the most damage or create the most risk, so we can start doing something? Because we're all going to go home tonight with nightmares and saying, well, we're all doomed, right? I mean, we can't touch anything without without ingesting plastic. So that's not good enough, you know.
Yeah, so some early work like PVC is banned in drinking water plumbing now, because we know that PVC can leach chemicals and cause problems. So there has been tiny amounts of movement. There was an attempted treaty, international treaty, much like the Paris Climate Agreement. There was an attempted plastic treaty about 2 weeks ago, but it fell through. That's not surprising. Like one of the few policies that seems to have been rolled out was to get rid of plastic straws, because there was a particularly heartfelt turtle video where they pulled a straw out of its nostril, and that led to this huge change. We're all wearing plastic clothes, but we're going to get rid of our plastic straws. But Donald Trump recently got rid of that law. He wants to go back to the plastic. So some of the little ground that we've made is getting undone in the current political climate, which is challenging. If I was to tell you one policy that I would love to see is a plastic tax. I'd love to see a tax on plastic, and I would love to see that money go straight towards sustainable fabric alternatives. Like we grow cotton in Australia. Sometimes we don't grow it in the right way, but I would love to see the plastic tax money subsidize greener cotton and wool to make those clothes more affordable. I would love to see you pulling some economic levers to help people make the right decision with things like that. Support our farmers, support Australian made, and support green materials whilst taxing imported plastic materials made of crude oil. That seems like a really simple policy we could roll out.
I think I've got perhaps a related question here online with that. Linda is asking, has anybody provided or are there lists of various household products that are not made of plastics? Because obviously part of this is we're talking about what are the alternatives that we've got? And you've mentioned cotton and wool for clothing, etc. So, knowledge is a key thing.
Yeah.
For people to be able to choose what they do. And do we just not have that information?
Yeah, so actually my brother-in-law is a professor at the University of New South Wales, and he actually researches this space, which is, can we trust industries that put stamps on things to say, oh, this is a green thing, this is a safe thing, this is a plastic-free thing? And he basically goes to research this and says, we cannot trust it at all. Those little stickers that say rainforest safe, he's gone to the forest and seen them being chopped down. So we cannot trust the private industry to come up with these stickers that say this is low plastic, this is no plastic. We will actually need a governing body to come in and say these are the plastic-free, low plastic pipeline products coming through. Yeah.
And who else is thinking, what's that sticker made of?
Yeah, exactly.
As you say
What's
that.
The worst example I've seen of that is individually wrapped prunes. Come on.
All right, we've got a question over here on the left-hand side.
Hi. You mentioned one of the biggest villains earlier in your speech was Coca-Cola. And they were involved in a lot of kind of lobbying against container refund schemes in and around Australia. You also mentioned that Tasmania was one of the last, most recent to go to a container scheme. And they did a split system. And they put out a overall administration and coordination. They put it out to tender, which a group called Tas Recycle handles. Now, one of their major shareholders is Coca-Cola. So would you like to be insightful and say, what's Coca-Cola up to now?
You're really not helping the mood right now. Yeah, so this is what we're up against. And this is why it's going to take more than an individual, us all acting in our best individual effort in order to combat this kind of stuff that we're going. But that's a great point. We're up against some big players that are going to buy the other side.
A question over here in the middle.
Thank you for the presentation. I was curious if microplastics were passed down from generation to generation.
I think that would be very hard because the plastic would have to get into the sperm or the egg. Maybe one particle in the egg. The egg is the largest cell in the human body and the sperm is the smaller cell in the human body. But I think it would be very hard. But there is this concept called epigenetics, and this is where changes in our DNA can actually be handed. So our experiences can change how our DNA is turned on and turned off. And that on-off switch can be inherited down into a generation. So there's no telling what the negative impacts of plastic might do to our epigenetic structures, which do get handed down to the next generation. Yeah.
What are the major health impacts or deleterious effects of the ingestion of plastic?
In humans, we're not sure. We've got that blood clot example, which I think is a very strong example of what microplastics might be doing, inducing clots. In humans, we're still learning, and we've got a laundry list of responses in mice. And the question is, do those same responses that are happening in mice happen in humans? We've seen things like increased DNA mutations, which is associated with cancer risk. We've seen inflammation, which is associated with cancer risk and scarring. And will we see dementia in the mouse models? That's still to come. That is research that is happening, and that's still to come. So we're in the dark a little bit. And as I mentioned with the question before that we had, there could be over 300,000 chemicals that we need to test. There's many, many polymers that we need to test. And so once we find one effect in one plastic, what about the next plastic? What about the next additive? We don't know. But that's a great question. We don't know. And that's what we're trying to figure out.
So I've just got one here online. how do we responsibly dispose of plastic products and clothes that we already own?
Look, all I can say is put it in the recycling bin, which is a grim thing to come to. What do we do with the plastic? Now, this is a controversial opinion that other people in my field don't have, but you mentioned biodegrading, right? Getting these bacteria to break down the plastic. Now, when the bacteria break down the plastic, if they actually use it for energy, because the plastic is full of chemical energy, if they use it for energy, I know that's not a chemistry term, but anyway, they will breathe out CO2. So when we talk about biodegrading, we're talking about taking long chains of molecules, breaking them down and oxidizing them, and then breathing out CO2. Now, there's a very fast way to do that, and that is in a 100% oxygen environment, you burn it, and that will turn the carbon chains into carbon dioxide if it's all going well. But the smoke, we don't know what's in the smoke, we don't know what's in the runoff, but I feel like that might be a better option in many situations than what's happening right now, which is it's leaking out into the ocean and getting into our water and getting into our environment. I'd be interested in your thoughts as the chemist on that.
Certainly, if you're going to burn things, you're going to generate particulate matter, in which, of course, the particles are the main thing. And in this case, often as a chemist, it's thought of chemicals bad, right? But it's probably, in many cases, it's not the chemicals, but simply the particle, as you're seeing in the comparison to silicosis and asbestosis. There's certainly going to be other aspects, and leaching of chemicals out of it, like bisphenol A is the example. Sorry, BPA. I don't like BPA and BPSs. There's too many acronyms. I like to think in chemical structure. But, there are lots of examples. Obviously, are there good chemicals and bad chemicals? Obviously, what is the one chemical that kills most people in the world every year?
Drowning?
Water. Obviously it's the amount of something and it's how it's used. But, we don't think of water as dangerous, but, it's responsible for numerous deaths every year. So, as I say, as a chemist, I've got to stand up for the chemical aspect of it. But, the chemical industry certainly, as you say, has had plenty of examples of trying to do good and ending up with bad. I'll give you a chemical example, morphine. Morphine's been known as to reduce pain, but it was known for its addictive properties very early on. So what did they do? They tried to make something better. They made heroin. So heroin was made as a way to try and remove the addictive properties, and heroin is many, many times more addictive than morphine. There's a lot of trial and error that goes on, but the key thing is the responsible use of what we do with that. I think we've probably got time for one more from the floor here before we have to wrap up.
Yeah, thank you. In the 1950s, the Merck manual was very useful. What can we rely on today?
I didn't catch that. Sorry. Can you go
the
one more
Merck
time?
manual, the book on chemistry?
The
came out annually.
Merck Index.
The Merck Index.
Called.
Sorry, yes.
So the Merck Index was effectively a dictionary for chemists, where you could look it up and it would tell you properties, hazards, physical properties, etc. And it will tell you that 97% hydrogen peroxide is soapy to taste, and I wouldn't certainly recommend taking that. Yeah. So I guess the question is there a book, or is there plans for a book to actually start to, or a resource to put this together for wider dissemination?
Yeah, it's very disorganized at the moment. Scientists are writing reviews of all the chemicals, but as I mentioned, it might be upwards to 300,000 chemicals. And I think really the onus should be on the producer, the discoverer, the inventor, the synthesizer, to establish in a very wide range of tests that it is safe. But we don't currently have that legislation. The closest legislation I could think to it is in the UK. They accidentally made coffee illegal during the passing of this legislation. But they basically said you need to establish that a chemical does not have psychoactive effects, and you need to prove it before you then roll it out. So you cannot get highs. And we're having these huge problems with people inventing synthetic cannabinoids all the time, synthetic marijuanas. So rather than chasing the tail, oh, you've invented a new drug, let's make it illegal. Oh, you've invented another recreational drug, let's make it illegal. England said, no, if it's psychoactive, you have to, it's automatically illegal and you have to go through approvals before you can roll out a chemical. So I feel like we need that sort of framework, but for plastics and plastic additives, you need to establish safety before using.
Okay, so look, we've come to the end of tonight's conversation. Obviously, we didn't get to all the questions. Apologies for that. So just to finish up the evening, please join me once again thanking Jack for sharing his expertise with us tonight and trying to get to as many questions as we could. And also thank you to everybody here in the Stanley Burberry Lecture Theatre and who've joined us online for the evening for taking part in tonight's conversation. And on behalf of the University of Tasmania, have a happy and safe evening and hopefully not too many nightmares tonight as we try and get to sleep. So good night. Thank you very much.